So let's put it all together. We now have, for main sequence stars, an understanding of the relation between, at least empirically, mass, luminosity, temperature, radius, and now we can hand this over to the people who modeled the sun and understood the rate of fusion inside the sun and predicted the neutrino flux, and they can adapt their models to study other main sequence stars and try to test the hypothesis that all of these main sequence stars are basically the sun at various sizes. So what do? We take a ball of hydrogen and model its behavior. We include all of the properties we know of hydrogen and of fusion and of convection and of radiation diffusion, and of course a star is a complicated system, but the idea is that a main sequence star is a ball of hydrogen which in its dense hot core is fusing hydrogen to helium, and you work on that assumption and then you see, will you predict the relation between luminosity and mass, between mass and radius, and mass and temperature that the main sequence obeys. And if you do, then you have an understanding of stars. And essentially, the point is that the conditions for hydrostatic equilibrium, together with the properties of the plasma out of which the star is made, determines everything, starting from the mass of a star. And I'd like to outline this. If this confuses you, skip it. But in the next slide, I'm going to outline how a stellar model proceeds in some rough level. So here's how we model a star. We start out with this picture here of a star. And what do we know? Well, I'm going to assume that I know the temperature outside the star and the pressure, the atmospheric pressure of the star. Effectively, the atmospheric pressure of the star is essentially zero, but I'll start with some small value. And I'm going to work my way in and try to understand from equilibrium how the temperature, the pressure, and of course, importantly, the mass density, rho, which I'm going to again say is very small on the outside, atmospheric, how these increase. I expect all of them to increase as I move in. So what do I know? A star is a complicated system, but I'm going to imagine, just for pretend, just so we get a sense of what's going on, that the interior of a star is an ideal gas. It's not. But if it were an ideal gas, then ideal gases satisfy the equation that we wrote down for this precise reason. PV is NKT, the product of pressure times volume is the number of particles times a constant times the temperature. I have pressure in here, that's good. I have temperature. I don't have density, but that's okay if these are all hydrogen atoms. And if M is the mass of a hydrogen atom, then since the mass divided by the volume is rho, and since the mass in a given volume is the number of particles times the mass of a hydrogen atom, I can relate N and V to rho, and I find that V divided by N, which is the quantity I get that enters into here, is simply N divided by rho. And so putting that into that equation, I find that P is equal to M times rho times KB times T. Okay, this is a version of the equation of state that I can use. And now what do? Now I need to impose, what this tells me, of course, is that as pressure increases, temperature and or density will increase. Now, that's one thing I know. And then what I'm going to do is I'm going to imagine I know the conditions right outside the star. Let's try to find conditions a little distance r inside. So this is the radius of the star, and I'm going to move a little distance r inside and try to see if you know what goes on here, how do you know what goes on there? And there are some things I know. I know the pressure here, P1, has to be bigger than P0. Why? Well, because I've sunk in. This layer underneath is holding up the weight of the bit of the star that is outside. So I can write some crazy equation that says P1 minus P0 times the area of the interface between these layers, which is 4 pi r squared, is equal to the mass of the gas in this region, which if I assume that its density is rho 0, that's also 4 pi r squared times little r times rho, that's the mass in there, and then I multiply that by g times the mass inside the radius r, so that's in this case the entire star, divided by r squared, and I can, from here, canceling these factors, I can find that the pressure change is r times rho times gm over r squared. Okay, now that gives me tells me that if I know the pressure here, I can tell the pressure there. I want to relate, figure out the density and the temperature in here. Of course, since the pressure changed, the density and the temperature had to change because the new pressure, which is higher, is equal to the product of the new density and temperature. There's another relation that I know, which is the important thing that I can put in is that I know the luminosity. There's a net flux of energy. The star is radiating at a luminosity L. And so that means that since the temperature of everything is constant, a net amount of energy, L, is being transferred through this layer at any given time. And if I know the properties of the layer, I can figure out how much hotter it has to be inside in order for an amount of energy L per second, a power of L, to propagate out. And how this works depends on what the mechanisms are. If it's convection, I need to use the convection properties of the fluid. If it's radiation diffusion, the radiation diffusion properties, conductive properties. But if I know the luminosity, I can figure out T1 minus T0. So this allows me, starting with T0, to figure out T1. And then I use this equation to figure out P1. And then I use this equation to figure out rho 1. And now I understand things one layer in, and then I can proceed in and build the entire model of the star one layer at a time. If this was not illuminating to you, just imagine that somebody models stars. So what do we learn? Well, the important thing is, looking way down in the middle of the star at the core, that I talked about the pp chain, which is how the sun produces energy. In stars with a mass of about 1.5 solar masses or more, so just above the sun, the core is hotter the bigger the star is because there's more pressure, there's more layers to integrate through and more mass. And it turns out that hydrogen at higher temperature can produce fusion in a much more efficient way through something called the carbon-nitrogen-oxygen, or CNO chain. This is a process in which the steps are many and detailed, and we don't need to go into them, and you can read up on them. But basically, the presence of carbon in the core catalyzes fusion in the sense that carbon fuses with hydrogen to produce nitrogen, which decays to leave carbon, a different isotope of carbon, which fuses again to produce another isotope of nitrogen, which fuses with another hydrogen atom producing oxygen, which decays to an isotope of nitrogen, which fuses with yet another proton, emits an alpha particle, and returns us to the original carbon atom. So the net result is 1, 2, 3, 4 protons go in, 2 weak decays take place, and a helium atom is spat out. The carbon is recycled in this process, so it's not being fused into anything. But at higher temperature, this process goes much faster than the pp chain. The point is that the rate at which this process goes is much more temperature dependent than the rate of the pp chain, basically because to start it all off, and at several stages in the middle, you need not to bring two protons close together overcoming their electrostatic repulsion. You need to bring a proton near to a carbon nucleus, which has charge 6, and that electrostatic repulsion is much stronger, and so it takes higher temperatures to get the CNO chain started. This is the qualitative difference between big stars and little stars. What are the results of this? Well, it turns out that what happens is that the mechanism by which all of these stars, main sequence stars indeed, can be explained as a ball of hydrogen fusing hydrogen to helium in its core. Details of the model depend on the size of the ball of hydrogen you start with. Very small stars with a mass less than 1/2 a solar mass, it turns out that there is no radiation zone as there was in the sun. There is just a convection zone. The entire star convects. This has importance for estimating their lifetime because remember, in the core, hydrogen is being converted to helium. Then this helium-enriched hydrogen bubbles up through the entire star, and new, fresh helium-poor hydrogen is convected down. So this star, when it runs out of helium in the core, when it runs out of hydrogen in the core, will essentially have converted a large fraction of the entire star to helium. And that's the way small stars work. medium mass stars, like the Sun, work as we described. The interior is a radiation diffusion region, and then the outer mantle is the convective region where hydrogen atoms are less ionized, they're therefore more opaque, and therefore they absorb the radiation, heat up, and then well up, and it's a hydrodynamic process of convection that brings the heat up to the surface of the star. In bigger stars, it turns out, convection and radiation are replaced. In these stars, the temperature is so high that much of the interior of the star is actually ionized, but in the interior, because there is a temperature gradient, the exterior of the core is still not as hot as the center of the core. The temperature gradient means that the rate at which fusion occurs changes very rapidly. This leads to such power differences in the power output between different layers that in fact the star becomes convective. So in a big star, the inner region of the star is heat is transferred by convection. So this region all gets mixed up. But the external region is in fact transfers heat by radiation. The fact that this is what's predicted by the models, and then predictions of luminosity as it depends on mass, and radius as it depends on mass, and temperature as it depends on mass, are reproduce the measurements from the main sequence, tells us that our models have it right. So we have an understanding of the basic physics of how main sequence stars work. They're a ball of hydrogen fusing hydrogen to helium at its core and transmitting the energy to the outside by convection and radiation diffusion, and then radiating that energy out. We are not going to reproduce all of the details of understanding the nuclear cross-sections that go into modeling, but I think we understand the basic principles, and the rate of fusion in the core, as we said for the Sun, is in equilibrium with the pressure, as we saw, applied by the outer layers, and therefore the mass determines the rate of fusion. And as the star sits on the main sequence, we'll see next week what happens before and after. But today, let's finish up by discussing what happens in the 10 billion years, say, for the Sun, that it sits on the main sequence. Remember, the Sun is about 4.5 billion years old, so it's about half done with its main sequence life. How does the Sun today compare to the way it was when it was a brand new, fresh, zero-age main sequence star, as we call it? So the Sun formed, it was mostly hydrogen. It had a core where hydrogen started fusing to helium. Over time, as fusion goes on, the hydrogen in the core becomes enriched in helium. So what that means is that if you have your star over here and the core in there, there is more and more helium in the core and correspondingly less and less hydrogen. This means that the probability for collision of two protons in order to initiate fusion decreases, because some of the time the protons are not running into each other, they're running into helium atoms, and in the Sun they do not have enough energy to actually fuse effectively with helium. And so the helium is inert, and there's less and less protons running into each other, so one would predict that the rate of fusion would decrease in the core. This would decrease the radiation pressure, because the pressure emanating from the core, large part of it is radiation pressure, all this energy. Furthermore, and this is it turns out to be the dominant effect, is that when particles undergo fusion, 4 hydrogen atoms are converted to 1 helium atom. And if you remember our PV equals NKT, what's really going on is the number of particles is decreasing, because 4 protons have only made 1 alpha particle. When the number of particles decreases, the pressure goes down. Now this cannot happen. The reason this cannot happen is because, remember, the pressure on the inside of the star was predicted and determined by the need to hold up the outer layers. How can the pressure decrease? If the pressure decreases, the outer layers of the star will contract the core. Now, this is the first time we're meeting this sort of a phenomenon that I called expansion by contraction, and it'll come back. It sounds like a weird economic theory, but it is a property of stars, and so I want to understand it this first time because it'll repeat many times over the course of our study of stars. And so what happens is the pressure does not decrease. Instead, the core contracts. So the material that was previously the core is contracted to a smaller radius. This, in turn, heats it up, both because we're converting gravitational potential energy. The entire star scrunches down, and so the entire star undergoes Kelvin-Helmholtz heating, and of course this is most extreme in the core. Moreover, because thermodynamically you contract something, it heats up. The temperature in the core rises and the density rises. How long does this go on? Well, until fusion rates increase enough to hold up the rest of the star. So, in fact, the pressure here is essentially equal, or larger, in fact, because of the contraction, to the pressure that previously obtained there, and densities and so on follow. In that process, something else happened. The region between what the core now occupies and where the core used to be didn't get evacuated. This is now occupied by an inflow of new hydrogen that used to reside just outside the core. This new influx of hydrogen is heated and compressed. It's now closer to the center of the star than it was before, and it in turn begins to undergo pressure. So there are two processes going on. One is the pressure in the core is maintained by compressing the core. This in turn heats the core, increasing the rate of fusion both by increasing the temperature and the density. And furthermore, the amount of fusing material grows because some of the hydrogen that was too cold and not pressurized enough to fuse is now contracting to the point where it begins to fuse. The net result is that the core heats, the fusing region grows, and the total power production of the star increases. When the core contracts, the luminosity increases. The increased power output from the core, in turn, applies extra radiation pressure and extra thermodynamic pressure to the rest of the star, and the star balloons out a little bit. So over the course of its main sequence lifetime, as it runs out slowly of hydrogen in the core, the star's core contracts and heats and accretes more hydrogen into the core, resulting in the fact that the outer envelope of the star grows and luminosity increases. This is a very important fact. So if we apply it to the sun, what does it tell us? It tells us that the sun now is about 25% brighter than when it formed, and this is halfway through its main sequence lifetime. The sun is now brighter than when it formed. 4 billion years ago, the sun was a rather dim star compared to what it is now. This meant that the Earth presumably was cooler. There are all kinds of complications trying to understand how this is consistent with what we find on Earth, but it is certainly what our stellar models predict. Moreover, we can run our simulations, and the core of the sun is now 60% helium. When I said it's depleted in hydrogen, I meant that. Of course, there are regions outside the core that are beginning to fuse as new clean hydrogen, untainted by helium, is compressed to the densities and temperatures where it too can begin to fuse, which is why the sun has a larger luminosity now. It's going to continue to brighten over the next 5 billion years, making Earth warmer and warmer, and you can ask, global warming, carbon dioxide, will the sun do us in? And yes, the sun will probably make Earth uninhabitable in, depending on your estimates, somewhere between 1 and 3 billion years. So if we manage to control our carbon emissions for that long, the sun will, in any event, doom life on Earth. This impact is a little bit imprecise because once you get into billion-year periods, there are other factors that come into account. The sun loses mass, and as it expands, the outer layers are now farther and farther from the center of the sun. Their escape velocity decreases, the solar wind increases. In its last couple of billion years, the sun's mass loss rate increases significantly, so that the Earth will be orbiting a star that is less and less massive, which means that with its current energy, it'll probably be propelled to a higher orbit. Once you allow orbits to change, you have to also remember that orbits in the solar system, I said, are stable to hundreds of millions, maybe a billion years out, but we do not have really reliable predictions that say that in a few billion years, there won't be some orbital resonance that will completely throw the orbits out of kilter. And so, a billion years out is a long time. We don't know exactly what will happen. But at some point in the next 3 billion years, Earth will probably be a problem. If we survive that long, we'll have to deal with it. Another busy week, but I think very productive. What have we learned by looking at the stars? For 90% of them, we have a pretty good physics understanding of how they work, and it matches all the data. And this came from decades of painstaking observation, measuring the positions of stars over the decades, to do astrometric measurements of binaries in proper motion, measuring the parallax angles of thousands of stars and computing their distance carefully, measuring thousands and thousands of spectra and classifying them and understanding the patterns. A lot of really, really careful observation, and then detailed numerical modeling with the advent of high-speed computing, and putting all that together with experiments on Earth to determine the properties of various nuclear processes. We actually understand a lot about how stars work. That's good for the 85% that are on the main sequence. What about the rest? Not all stars are main sequence stars. We need to understand where the rest come from. A related question, it turns out, will be, well, what was the sun like before it became a main sequence star? And even more excitingly, what happens when the hydrogen runs out and it can no longer be a main sequence star? And that is what we're going to start studying next.